Welding Institute, the World Centre for Welding Technology, situated near Cambridge. The site is home for a training centre for all areas of expertise in welding technology and non-destructive testing, the Institute's professional division, and the largest research and development laboratory complex in the Western world for materials joining and testing. The microjoining facility is one of the specialist sections of the Institute and is concerned with precision joining techniques for the electronic, electrical, aerospace and automotive industries. The facility includes a fully equipped laboratory and cleanroom, which are used for research and development work on microjoining processes, applications and problems, funded by research member companies and the United Kingdom government. The Class 10,000 cleanroom houses a range of commercial equipments commonly used by the electronics industry for package sealing, device interconnection and die attach. Die attach is the joining of a semiconductor device to a substrate. This equipment is capable of handling a range of die sizes and can attach them to a range of substrates, as shown here using gold silicon eutectic. Other materials used are two-part epoxy, silver glass paste and solder. Large area die attach poses problems, making the choice of attach material critical. Wires are often used to make the connections between semiconductor devices and their substrates or package leads. Wedge bonding is a widely used interconnection technique for silicon devices, and a detailed program to investigate the effect of bonding tool shape and welding conditions on aluminium wire bond quality has been carried out. A number of wire materials and diameters has been studied, including 7 micron gold, 25 micron copper and 500 micron aluminium. The unidirectional nature of the wedge bond, as illustrated here using 200 micron aluminium wire, is a disadvantage when automation of the welding process is required. Ball bonding, here using the same aluminium wire, is very much easier to automate because the wire comes off vertically from the first bond and can therefore be led off in any direction to the second bond. Until recently, ball bonding was restricted to gold wire, but this can result in the formation of weak, high-resistance intermetallic compounds at the bond if used on aluminium metallization. Development work at the Institute has enabled good quality bonds to be formed on aluminium and copper wires. This is achieved by capacitor discharge in an inert gas shield. Good quality bonds down to 50 microns in diameter have been made using 17 micron diameter gold and copper wire. Aluminium, gold and copper ball bonding techniques are also being investigated on automatic wire bonding machines, shown here. These are capable of bonding speeds of up to 3 loops per second. Bond quality is usually assessed by destructive testing. A shear test is carried out on ball bonds. As can be seen, a shear tool is used to remove the bond from the substrate, and the load to do this is noted. Wedge bonds are tested by carrying out a 30-degree pull test. There is a growing interest in multi-parameter in-process monitoring of wire bonding machines. Work is being conducted at the Institute to develop such a system. In this example, a laser interferometer is being used to detect the vibration of the wire bonding tool as bonding is carried out. Simultaneously, other parameters such as wire deformation, force, voltage and current are also recorded. An alternative technique for the interconnection of electronic devices is tape automated bonding, or TAB. Instead of making each connection individually, Tab speeds up the process by making them simultaneously. The required interconnections are etched onto copper foil, which has been attached to 35mm wide polyimide film. The inner leads are thermocompression bonded to the bonding pads on the silicon die, with usually gold or gold tin as the intermediary material. The outer leads are then positioned and attached to the substrate in a similar way by thermocompression bonding or reflow soldering using lead tin solder. Once devices have been interconnected, they are generally sealed inside a package which may be of plastic, ceramic or metal. Resistance seam sealing is a common technique for hermetically sealing large metal packages, which are often used in high reliability applications. Welding trials have been carried out on both gold and nickel plated Kovar packages with both stepped and flat lids. Helium leak tests, pressure tests and temperature measurements taken within the package during welding have been used to assess the joint quality and the possibility of damage to electronic components within the package. Metallurgical sectioning shows that the joint formed by this technique is not a fusion weld, but a braze formed using the plated coating. An alternative sealing technique is laser fusion welding. This 300-watt neodymium YAG laser operates at a wavelength of 1.06 micrometers and is being used here for welding gold-plated Kovar packages. The XY table is microprocessor controlled and enables welding to be carried out at a constant speed even around corners. Like seam sealing, the heat input during welding is low and the circuitry within the package is not exposed to temperatures in excess of 125 degrees Celsius during welding. The laser process is, however, more versatile than resistance seam sealing, since dedicated machines are not necessary and lasers can easily be used for other welding and machining operations, such as scribing. Laser soldering applications are also under study. Here, solder pads are deposited using silkscreen process printing equipment. Following which, devices are positioned, ready for the reflow soldering operation. Another property of the neodymium YAG laser beam is that it can be fed through fiber optic cables. Shown here, one laser head is supplying 3 outputs to a component where spot or seam welds can be made simultaneously, counteracting any movement or distortion resulting from contraction of weld metal or uneven heating. A 4th fiber can feed another workstation, or the one laser can feed 4 stations. The flexibility of the 5-meter-long cables also allows awkward joint geometries to be welded. An alternative fusion technique for spot and seam welding small components is tungsten inert gas arc welding, or Tig Welding. The equipment shown here is capable of delivering up to 75 amps arc current in either a pulsed or continuous mode. Applications include diaphragm and bellows welding, transducer body welds and package sealing. Tig welding can also be applied to very small components. Here we see a 75 micron diameter insulated copper wire being spot welded to a pin. This type of joint can be applied to a range of wire welding applications, including transformers, resistors and armatures. A range of capacitor discharge, AC and DC resistance welding equipment is available in the laboratory for spot, crosswire, butt and seam welding. A transistorized DC power supply gives full control of resistance welding parameters, enabling consistent welding of awkward joints. Here is a gold-plated Kovar lead frame being joined to a substrate. Copper and aluminium foils and wires can be spot welded using this ultrasonic welding equipment. The parts to be joined are clamped between the welding tool, or sonotrode, and workstation, and a pulse of ultrasonic energy is applied. The frequency of vibration is 36 kHz. A solid phase joint results. By overlapping a series of spot welds, a seam weld can be made. Percussive arc welding is a technique used particularly for butt welding wires onto resistors and capacitors, and for contact welding. It can be used to join dissimilar metals such as copper to steel. The process involves bringing the two components rapidly together and discharging an arc to melt the joint interfaces just before they touch. Percussive impact follows and a weld is formed. Microfriction welding is particularly suited to the joining of dissimilar metals, which are difficult to weld by other techniques. This industrial prototype, developed by the Institute, can weld studs between 1 and 3 mm in diameter in approximately 1 second. Good quality welds are possible because of the restricted diffusion which occurs during friction welding. Welds between various material combinations are shown, including stainless steel to aluminium, stainless steel to carbon steel, copper to aluminium, copper to steel, steel to covar, and copper to copper. This is an in-vacuum electrostatic and diffusion bonding equipment, which has been built at the Institute. Electrostatic bonding is a solid phase joining technique used for the assembly of pressure transducers and solar cells. The bonding of glass to silicon or glass to metal is achieved by applying a voltage across the component whilst it is kept hot and under pressure. Here, Pyrex is being bonded to silicon using a temperature of 300 degrees Celsius and 1 kilovolt. Bonding times are typically from 1 to 5 minutes. This process can be used to bond silicon wafers containing hundreds of pressure transducers to glass discs which are subsequently sawn into individual devices. Diffusion bonding is another solid phase joining process which uses just heat and load to make a bond. This gold metallized beryllia heat spreader has been diffusion bonded to a copper heatsink. In addition to microjoining process studies, the Institute is actively engaged in developing new non-destructive testing methods for surface mount devices and microscopic joints. Methods under consideration include microfocus radiography, seen here in use for the examination of a eutectic die-attach joint. And thermal imaging, which is promising for solder joint inspection.
New developments currently being investigated are ribbon bonding and encapsulation of electronic devices with thermoplastic lids using ultrasonic techniques. Ribbon bonding has potential for interconnection of high lead count, small pad size, advanced electronic components, especially in small batch production. The use of ribbons may offer an alternative to wire bonding and tape automated bonding, as it can combine the flexibility of wire bonding with the mechanical and electrical characteristics of lead frames. This is attractive, as wire bonding equipment can easily be adapted for ribbon bonding, and the need for bump chips or tape and tooling charges for lead frame manufacture is eliminated. The thermoplastic encapsulation weld is formed using ultrasonic energy to generate sufficient heat to melt a projection on the lid or base structure. In this case, an injection moulded lid is being welded to fine-pitch, gold-tracked FR4 substrate. The lid is placed in a tuned horn mounted on a 20 kHz welding machine and pressed onto the substrate. whilst ultrasonic vibration is applied. In this case, the package is welded in 2 seconds using a vibration amplitude of 78 microns and a force of 600 newtons. Ultrasonic thermoplastic encapsulation has been achieved on a range of packages including lead frame, epoxy glass and polyamide PCB, polyamide tape and thermoplastic substrate. This packaging technique is attractive because it fills a gap between expensive hermetic metal packages and cheap plastic injection mouldings. With the correct choice of materials, it should achieve better hermeticity and reduce stress at a fraction of the cost of metal enclosures.
Member companies can obtain further information about any of these techniques by contacting the staff of the Microjoining section of the Welding Institute.